Dear learners, greetings from IIT Guwahati. I welcome you to this course Applied Thermodynamics. It is being offered under MOOCs platform by Center for Educational Technology IIT Guwahati. So, we are in the first module, that is module 1, and in this module we will discuss about the basic aspects of thermodynamics, and this title of this module I have kept it as a review of basic thermodynamics. So, under this topic the following components will be covered. The first lecture will be thermodynamic systems and pure substance. Second lecture would be heat and work transfer. We will discuss about laws of thermodynamics, and third one will be concepts of entropy and exergy. Please remember, these are the review concepts. So, we will basically give importance to the basic understanding that has been covered at the UG level. Now, in the first lecture, that is thermodynamic systems and pure substances, I will touch upon the thermodynamic systems with its basic terminology, properties, then we will discuss something about pure substance. So, let me start the word thermodynamics, how it comes from. So, as I mentioned in my first introduction lecture, thermodynamics is nothing but the conversion of heat and power. So, mankind has been habituated with different source of energy and its requirements in various forms. So, they are electrical, thermal and mechanical, and for all these things the very basic bottom line is the thermal energy, and which is in the abundant form, and we also need to know how to convert the thermal energy into various forms, and for this conversion we require some kind of fundamental laws that we get from the basic concepts of thermodynamics. So, the word thermodynamics has two components, and they are from the Greek words, that is thermi, which means heat, other is dynamics, which means power. So, basically it is a conversion of heat into power. This thermodynamics is mainly classified as classical thermodynamics and statistical thermodynamics. Statistical means you do go with a very microscopic approach, and classical thermodynamics goes in a macroscopic approach. By macro and microscopic approach, I mean when a gas is contained in a cylinder as shown in this figure. So, in a microscopic approach we will say its state is at pressure, it has certain pressure, certain P, volume V and temperature T. But when you think this gas in a microscopic approach, then we have to divide this entire container into coordinate systems, that is x, y, z, and we are looking about every molecules minutely and its locations and corresponding its pressures. So, likewise for the molecule I, whose coordinate is xi, yi and zi, we say its pressure is pxi, pyi and pzi. So, likewise all other parameters can be defined, but however our approach in this course would be a macroscopic approach, where we are looking at the global behavior of a given situation. And as you saw that this course is about applied thermodynamics, so it has a lot of application areas, and in fact this particular course is mainly deal with different power plants, internal combustion engines, aircraft engines, cooling systems, which means refrigeration and air conditioning. In fact, human body has lot of thermodynamic systems which is governed by its principle. So, let me give a basic terminology. When you deal with the thermodynamic systems at UG level, you must have come across many such terminology, and which are available in many fundamental textbooks. So, I will touch upon some of them. First is system. In the thermodynamic sense, when you say it is a system, it is nothing but a quantity of matter or region in the space chosen for the study. For example, in this figure, if you have a system, that means this particular colored region has been chosen for our user attention. So, if this is our system, then apart from the system, rest of the things are called surroundings. and the system plus surroundings constitutes a universe. So, this is all about the fundamental definitions of system surroundings, and in fact obviously this system and surrounding must have a boundary. So, we call this as a boundary. So, this boundary could be a flexible boundary or it could be a fixed boundary. So, this is how it is defined in the form of thermodynamics. Then we have come across different types of systems in thermodynamics. One is closed systems, open system and isolated system. So, what does this mean basically in our terminology is that when you talk about a closed systems, normally when you say the system can have mass interactions, it can have energy interactions or it can have both. But when you say it is a closed systems, it is we have to say there is no mass interactions, but energy interaction is possible. And typical example could be given as a piston cylinder devices, where a certain volume or certain quantity of mass is always compressed or expanded in certain region. So, that means there is no mass interactions, there is no mass coming into it, but it can do energy interactions. While doing so, what happens? The gas is compressed. So, it is compressed, and in some situations its temperature goes up. So, there could be energy interactions in the form of heat. So, when we do not have mass interaction, but energy interaction is possible, it is a closed system. But when we have both the system, both the things possible, that there is as mass interaction as well as energy interactions, then we call this as a open system. Now, in some situations or a special case when there is mass, there is no change, no mass and energy interaction is possible, then we call it as a isolated systems. And in our terminology, normally when we say it is a open system, we have a control volume approach. So, we call this as a control volume. So, the volume or space under the chosen for the study, we call this as a control volume. The other terminology could be is the state postulates. State postulates means when a system is at a given situation, if you want to define a system, we have to give some name to it. Here we name, I mean coordinates of the system. So, coordinate of the system could be its property. So, the number of properties that are required to fix the state of a system is known as states postulates. A typical example could be a simple compressible systems which requires two independent properties, mainly pressure, temperature or volume, specific volume. So, these are the required to fix the state. Then we have a homogeneous and heterogeneous systems. So, any system can exist in three phases. So, it can be solid phase, liquid phase or gas phase. When you say homogeneous system, that means it contains a single phase, there is no multiple phase in the present in it. So, it is a homogeneous system, but when the system has more than one phase, then we call as a heterogeneous systems. The next word that we are going to use frequently is the thermal equilibrium. So, it refers to a state of a system where having a thermal equilibrium, it refers to a state of a system when there is same temperature throughout. It also has mechanical equilibrium and it also has a chemical equilibrium. So, basically thermal equilibrium has three components. One is its temperature is throughout, same throughout. When you have a mechanical equilibrium, it has no unbalanced force, and when you have chemical equilibrium, we have no chemical reactions. So, the word, instead of using thermal, I will use this as a thermodynamic equilibrium. So, this thermodynamic equilibrium has three components, that is thermal equilibrium, mechanical equilibrium and chemical equilibrium. So, in most of our situation when we will talk about thermal equilibrium, which means that for a given system, if you look at a particular system and it contains maybe a gas, but this container has a non-uniform temperature at T is equal to some time instant T1. So, let us say at different locations we measured the temperature had different values like 42, 30, 28, 26, but that is at time t is equal to T1. Now, when it goes to a thermal equilibrium, we expect that entire container will have uniform temperatures throughout or same temperature throughout, let us say 25 degree. That means, at T is equal to T2, the system attains thermal equilibrium. Then next terminologies are state, path, process and cycle. So, the state of a system means it has a definite value, and definite value I give in terms of its properties. So, when the properties are nothing but the coordinate of the states. So, for example, in this particular PV diagram, if I want to define a coordinate pressure and volume, that is point 1, that is the state. So, that is the state of the systems. Now, in another situations, the state of the system change to point 2, where the coordinates also change. In this way, there is a change in the state. So, that is called change in the state. Now, while changing its state, it can follow different path. So, path could be A, B, C, and for different path it can have spend most of its energy in the form of work or heat. So, the path could be A, B, C. So, that means from 1 to 2 we can have infinite ways we can reach from 1 to 2. This is called as a path, and when a path is completely described, that means if you can give the path as a form of equation, then we call this as a process. So, you have to say that 1 to 2 I can have a process A, I can have also process B, or I can have a process C. So, this is what we call as a process. That means, this path is completely specified. Then cycle. So, what do you mean by cycle? That means, when a system from its initial states goes to a final states and then come back to its original states. So, in this process it comes a cycle. So, for example, in this particular figure, the system point state 1 goes to state 2 in a path B, but on return also it comes to another path A and comes back to original states. So, in this way we say it is a cycle. So, this series of state change in which the final state is identical to the initial state is known as a cycle. Now, in the thermodynamic systems, many a times we will come across a word which is called as a quasi-static. Quasi-static means it is a infinite slowness of a system. So, it is a very slow process, and what does this mean thermodynamically to us? That if you want to explain this, let us consider this particular figure. So, we have a particular piston cylinder system device in which there is a weight which keeps this piston in balanced positions. So, its initial state I can make that it is the point 1, I can give the initial state. So, this system is in equilibrium because the gas which is in the bottom of the piston is given by exerts a force on the bottom of the piston, and this is balanced by the weight which is acting on it. So, in this way we say that this initial state of the system is point 1. Now, another way I am looking at that, if I remove this weight instantly, then I can come back to the same state to a state 2, but in this process it will not be quasi-static. So, to define a quasi-static, what I will say is that I will assume that this particular total weight W can be divided into small segments of weight of very small mass, and each time I will remove one mass, so that there is a very minute change in the system. So, the next equilibrium state which I can achieve is here. So, that means if I remove the first layer of weight, the system goes from 1 to the first star. If I remove the second layer of mass, the system goes from the state 1 to the second star. So, likewise the process will follow in a particular slow fashion, and finally it is going to land in the point 2. So, this particular process is a quasi-static process, but had I removed this weight instantly, then this process would have reached very instantaneous manner, and this is not qualified as a quasi-static process. So, this dotted line I will refer as a non-quasi-static, and the path that is followed through stars, they are given as a quasi-static process. Then comes back to thermodynamic properties. So, when you talk about properties, in fact, these are nothing but the coordinates of the state, and in the sense of thermodynamics, we define in two categories, one is intensive properties, other is extensive properties. So, what do you mean by intensive properties? So, intensive properties are independent of mass and size. So, typical example could be pressure, temperature and density. So, they are not dependent, and extensive properties depend on the size of the system, that is mass dependent. And of course, extensive properties per unit mass we call it as a specific properties, and so they become intensive. For example, specific volume becomes an intensive properties, whereas volume is a extensive properties. Similarly, specific internal energy is an extensive properties, specific internal energy is an intensive properties, but internal energy is only extensive properties. A typical example could be given in this way, that how do you distinguish an intensive and extensive properties. For example, if you look at a container having a certain gas and it has a mass m, volume v, pressure p, temperature T and density rho. So, what you do is you insert a physical partition into this container. So, in such a way that entire volume becomes half. So, volume becomes V by 2, mass becomes m by 2, but what remains unchanged, that both partitions will have same pressure, same temperature and same density. So, that means these three properties do not change through this partition. So, they are called as intensive properties, whereas what changes, mass and volume. So, they are extensive properties. So, that means they depend on the size of the system. Next important criteria or important property that we deal with the energy, because the thermodynamic is nothing but the energy conversion from one form to other. So, how do you define this energy? And in fact, it is also considered as a very important thermodynamic properties. So, it is nothing but the potential of the flow that can exist in various form, chemical, electrical, mechanical, thermal, nuclear, etc., but we will be mainly focusing on the thermal part. So, these energies also can be viewed as a macroscopic energy or microscopic energy. So, macroscopic energy is related to the global behavior in the form of kinetic energy, potential energy, whereas microscopic nature would depend on the molecular structure and degree of molecular activities. In fact, kinetic theory of gases are the examples in which we deal with microscopic form of energy. And very important energy that we are going to come across is the internal energy. In fact, this internal energy was introduced when you discuss on first law, and it is nothing but the sum of microscopic form of energy with respect to molecular motions. So, it could be translation, vibration and rotation, but we are looking as a whole in all this microscopic form of energy as one global form, that is internal energy. And later on we will see that from the first law we will say that this internal energy is nothing but it is a function of temperatures. The portion of internal energy with respect to kinetic energy in molecule is called as sensible energy. That means, the molecular motions have some energy in the form of their motion, that we say it is a kinetic energy of molecules. So, they are considered as a sensible energy. So, internal energy has two components, one is sensible part, other is the binding force of the molecules with respect to phase change. So, this particular component we call as latent energy. So, internal energy are two components, one is sensible energy, one is latent energy. So, these two are very important, and when you sum it up will give the total internal energy of the system. And more things will be clear when you clear about this internal energy in the form of latent energy or sensible energy when you deal with the pure substance. So, what do you mean by a pure substance? So, a substance that has a fixed chemical composition throughout is known as a pure substance, and in our thermodynamic sense we have categorized them as liquids or gases. So, in the very common liquid is our water, and gases that are available with us is nitrogen, helium, oxygen, all these things are called as a pure substance. And all these pure substances, they have three principal phase, that is solid, liquid and gas. Now, when we say it is a pure substance, there are some situations where two or more phases can coexist. That means they are in equilibrium. So, that is also possible, that there are possible situation where two or more substance can be in equilibrium. And typically when you say that in what are the different forms in which the substance exists in nature. So, they are in either compressed liquid or subcooled liquid. So, this is nothing but the what we mean as a liquid state. It can be a saturated liquid, it can be a saturated vapor, or it can be a superheated vapor. So, these are the fundamental existence of a pure substance in nature. So, this is applicable for all types of substances. Now, here when we have a liquid state or vapor state, so that is what the importance of internal energy comes into picture. It can have a latent energy or it can have a sensible energy. So, as I mentioned earlier, so sensible energy is associated with the random molecular kinetic energy of the molecules. Latent energy is associated with respect to binding force among the molecules. So, basically when you change the state, that means solid to liquid, there is a physical phase change, then we say it is a latent energy. But here the word energy we are now going to replace with heat, because this energy is nothing but it is in the form of heat. So, the amount of energy absorbed or released during a phase change process is called as a latent heat. So, during melting or the energy released during freezing is known as latent heat of fusion. The other term that we are going to use in the case of vaporization, where the energy could be absorbed or it could be released during condensation, is known as latent heat of vaporization. So, let us explain how different state of a system is possible in thermodynamic coordinate systems. By thermodynamic coordinate system, I mean it is pressure, temperature and volume. So, you have to keep one as a constant and plot the other two parameters. So, for example, if you take a pure substance of water and we are plotting this water, different state of water in a temperature volume coordinates. So, at 1 atmosphere, that means a normal atmospheric pressure, when we say water at 20 degree centigrades, we say it is a liquid state. So, it is a liquid state, and in our term either we can say it is a compressed liquid or subcooled liquid, whatever way we can thermodynamically we can tell this. So, it is a liquid state. Now, if you keep on increasing the temperature, it goes to a state 2. That means, when you reach 100 degree centigrades for water, so it is in the saturated liquid state. So, point 2 is in the saturated liquid state, but still it has not it is about to vaporize, but it has not changed its state to vapor. So, we call this as a saturated liquid state. Now, if you keep on further increasing the temperature, then the liquid has to change its state. That means, this binding force has to be broken by adding more and more heat. When you keep on adding more and more heat, the temperature does not change, but its liquid changes its state to vapor. So, at any arbitrary, and this will keep on happening till the state 2 reaches to state 4. So, when you state 4, that means entire liquid which was at state 2 has now comes to vapor state. So, this is at the state 4, but what happens in the intermediate between 2 and 4? So, 2 and 4 in between 2 and 4, that is another state, that is state 3, which is in the liquid vapor mixture state. So, this is the state 3 is the saturated liquid vapor mixture. It is a liquid vapor mixture state. Now, from 4 again we keep on adding heat, then what will happen is we will reach the state 5, where it is a single phase system, it is what we call as a superheated vapor. So, this is all about that different 5 thermodynamic states that happens on a single line, and this is only at 1 atmosphere pressure. Now, if you keep on increasing the pressure, this line will go up. So, this is how we define this different state of water, that is from 1, 2, 3, 4 and 5, and this has been plotted for 1 atmosphere. Now, if you change this pressure, that means, and we will define some parameter what we call a saturation pressure and saturation temperature. So, saturation pressure and temperature, I mean when you are at the saturated state, that is at 0.2 or 4. So, these are the nothing but the saturation temperature is 100 degree centigrade. So, when you say saturation temperature is 100 degree centigrade and pressure is about 100 kilopascal, that means it is about 1 atmosphere. But when the temperature is saturation temperature is 150, the saturation pressure also goes up. So, we can have a plot, that means saturation pressure increases with the respect to saturation temperatures. Now, moving further, if you extrapolate all these data for all sorts of pressure and temperature, we will have a dome, and this dome what we call as a temperature volume diagram, and normally we call this as a property diagram. So, the variation of properties during a phase change process are studied through property diagrams. So, this property diagram, when you look at liquid and vapor mixture and all saturated points, if you draw them and prepare a locus, then it will form as a dome. So, what we have seen here, so if you look at the first dotted line where pressure is P1 and the second pressure line P2, that is P2 greater than P1. So, this length of the straight line which is in between dome is reduces, and if you keep on increasing the pressure, this entire line becomes a point and what we call as a critical points. So, basically in this saturation line we can have two distinct zones, one is saturated liquid line, other is saturated vapor line. They are separated by a point what we call as a critical point, and beyond this dome we have a compressed liquid region, and beyond the saturated vapor line dome we have superheated vapor region. In between the dome we call this as a saturated liquid vapor regions. So, this is all about temperature volume plot, and we can replicate the same figure in the pressure volume plot, pressure specific volume plot. So, here the lines will be just reverse. So, but in the and temperature line T2 will be as you go up, the temperature line also keeps on increasing. And for water, these critical point coordinates would be 22.019 megapascal, 374.14 degree centigrade and 0.003155 meter cube per kg. Now, if you extend this particular property diagram with respect to solid phase, what is going to happen? This similar pressure volume plot can be plotted. Now, here when you have solid phase, when we are introducing, we will have a, after this drum we will have a line which is solid plus liquid and which is another is purely solid, and there will be another line which is called as a triple line, and this triple line will separate solid with respect to vapor. And here there are two plots of P in the pressure volume coordinates. One is the substances that expand during freezing and the substances that those contract during freezing. So, here the basic philosophy that lies here, that entire pressure volume diagram now is replicated in another diagram, which is pressure temperature diagram, where this triple line becomes a point. So, the main importance of this diagram is that it can clearly distinguish the different phase of a pure substance, that is solid, liquid and vapor. And all these things, like we have discussed about melting, we have discussed about vaporization, and we are going to discuss about sublimation. That means, a substance can go from solid to vapor through a process that is called a solid sublimation. And all these three lines, they exist at a point in a pressure temperature diagram, and we call this as a triple point. So, at the triple point, all the three phases of a pure substance coexist. That means, at that point we can see, we can have a substance in the solid as well as liquid as well as gas. Okay. So, here the importance of this pressure temperature diagram, because it gives a triple point. So, the main important things that I am going to emphasize here, that when you look at actually the pure substance that are available in nature, in some substances they have the triple point pressure temperature coordinates as above atmospheric, and most of them have below atmospheric. For example, if you have atmospheric pressure of 101 kPa and 298 Kelvin, and if you look at water, nitrogen, oxygen, carbon dioxide and acetylene. So, all these four categories, if you try to compare, we can see that acetylene has a value close to the atmospheric value, but all like water, nitrogen and oxygen, they have triple point value much less than atmospheric. But one significant thing that we can see is the carbon dioxide. So, it has a peculiar characteristics of triple point value, that is 2116.55 Kelvin and 517 kilopascal. So, this makes us a thinking that we can create, we can that means, if you look at carbon dioxide, this carbon dioxide can be thought of existing in two phases, one is solid phase, other in gas phase through sublimation process, and in our commercial term we call this as a dry ice, and which are being used in many commercial applications. So, this is how I want to emphasize about this pressure temperature diagram. Now, we will give some introduction about property tables. So, when you deal with the property tables, I told that how many coordinates are required to fix the state. So, first thing is that we are in the saturated liquid state. When we are in the saturated liquid state, we require just one parameter, either pressure or temperatures, or if you look at saturated vapor also, there also you will require either one temperatures. So, this is how we say that 100 kilopascal is sufficient to say that whether we can have a saturated liquid or saturated vapor state, and it has two values, the specific volume value Vf and Vg. Now, when you are intermediate points, that means when we are in the saturated liquid vapor mixture region, that is in this dome, then we will have some intermediate points in which can be calculated through linear interpolations. So, the average properties values, let us say at point B. So, point A is the saturated liquid state, point C is the saturated vapor state, its specific volumes are defined as Vf and Vg, but average property at point B can be defined as a Vfg, which is nothing but we can define a parameter x, that is AB by AC. That means, through linear interpolations from this distance we can calculate this x, and this x we call this as a quality of the substance or dryness fractions, and in our steam table term we call this as a quality of the steam. And of course, at this state its specific volume value will be higher than the saturated liquid value, but lower than the saturated vapor value. So, this is the equation that we are going to use when we are going to define the average value of saturated liquid vapor mixtures. So, here once you have average value of saturated liquid vapor mixture, then we can also have internal energy, we can also get the information for average values of enthalpy in the liquid vapor region. Now, let us see when we are in the compressed liquid region. So, when we are compressed liquid region, typically we are in the beyond this zone, that is beyond this line, and at this stage we just require the temperature at which it is defined. For example, if you want to calculate the internal energy, we can say internal energy at 80 degree centigrade, that is sufficient because you require only one coordinates. And when we are in the superheated region, that means when we are going beyond the saturated vapor curve, that means for example, at these particular locations, if you want to find a coordinates, its value, enthalpy value is much higher than the its saturated vapor value. So, here we require two coordinates, one is the pressure, other could be any temperature or any other parameter to define its state. So, it is a single phase region. Now, whatever things I have explained, if I want to summarize, I will summarize in the properties of pure substance in two forms. One is in the form of steam table, other is in the form of Mollier diagram. So, the first thing is the Mollier diagram. I mean, in our thermodynamics course, we will be mostly covering this using the word Mollier diagram, which is nothing but the enthalpy versus entropy curve. So, the enthalpy versus entropy curve, when it is plotted, if you can see in this particular plot, there are different constant pressure lines, constant volume lines, all these things are given, and this is very bottom line philosophy for calculation of properties of steam when you are using this for steam power plants. So, it is very easy to calculate because it does not require any interpolation. From this coordinate you can fix the any two parameter. If it is given to you, you can locate that point, and when we are locating that point, then we can rest of the parameters can be found out. The other way people look at is in the form of steam tables. So, when you have steam tables, it has three parts. One is saturated water table, saturated water for temperature table, saturated water for pressure table, and saturated superheated water vapor table. So, for temperature table, if you look at, the temperatures are given, corresponding saturated pressure also given, and all the rest of the properties are noted here. Similarly, in the saturated pressure table, pressure is given first, that is followed by temperature, saturated temperature, and subsequently all other properties. Now, when you deal with the superheated vapor, it has two important coordinates. One is you require a pressure and corresponding temperatures. So, this is what about the pressure, and these are the temperatures. For example, in this case we have a 10 bar pressure and the temperature could be 280, 320 and 360 degree centigrades, and corresponding value maybe this is, I think these corresponding values of internal energy, enthalpy and entropy are noted here. Okay. So, these two are the extracts from the very fundamental book Moran and Shapiro. So, from these books, probably in our while solving the problems, we can use the data from this referred table. And last component of this lecture is the gases. So, when you look at the gases, so this is the last part, we are looking at the liquids. Now, when you are looking at the gases, so gases normally follow ideal equation gas or equation of states. So, if it is a properties of pure substance, if it is a gas, it follows a fundamental equations Pv is equal to RT. So, P here P and V are specific volume, R is the characteristics gas constant, A is the temperatures. Another way of looking at P into total volume is MRT, and here also we are going to introduce universal gas constants when we are dealing with kg mole, and mostly these particular notations were used for the chemistry people, where they use the universal gas constant. But in our routine approach, either we will be using air or water vapor or something. So, in that case we are mostly concentrate in the other form, that is simple form, that is equation of state Pv is equal to RT. Okay. So, also we can introduce the universal gas constant Ru and molar mass or molecular mass m. So, if you look at the per unit mass basis, we can define them meter cube per kg. If you are defining per unit mole, then you can define as meter cube per kilomole. Okay. So, there we have to use the word universal gas constant, but in normal routine practice, when you are using per unit mass basis, we are okay with the simple mass based systems, not molar mass system. So, let me solve some problems which we have covered in this particular course. So, the first problem is based on a property called as pressure. So, when you deal with the pressure, this could be in two terms, one is absolute form, other may be gauge or vacuum, and reference is P atmospheric. So, when any pressure is measured with respect to atmospheric, then and its value will be, we can define as P gauge or P vacuum. But when the actual pressure is calculated P absolute, it may be P atmospheric pressure plus P measured pressure. So, this either it could be this measured pressure could be gauge or vacuum. Now, when we say gauge, it is above atmospheric, when we say vacuum, it is below atmospheric. So, absolute pressure can be further written as P atmosphere plus P m or P atmosphere minus P m. Okay. So, this is all about the concept. Now, for this particular problem, what has been given to us, that we have a manometer and it is used to measure the pressure in the tank. So, what is given is fluid has a density, specific gravity as 0.88. So, pressure can be written as P is equal to rho g h. So, rho can be found out specific gravity into density of water. So, in this case density of water is 1000. So, specific 0.88, gravity is 0.88. So, it will be 880 kg per meter cube. So, h is given as 520 mm. So, g is 9.81 meters per second square. So, we can calculate P from this data as 880 into 9.81 into 0.52. So, this turns out to be 4.5 kilopascal, and this 4.5 kilopascal, if I say, it is gauge because it is positive. So, if you make absolute, so I have to add atmospheric pressure, that is 101.325 plus 4.5. So, this turns out to be 105.825 kilopascal. Okay. Now, next problem that we are going to solve. So, the next problem that we are going to discuss is that we have a rigid tank and it is at 90 degree centigrades and it contains 8 kg of water. Out of this 8 kg of water, we have 6 kg liquid and 2 kg vapor. So, basically we know mass of MF as 6 kg and mg as 2 kg. So, from this we can calculate x, that is dryness fraction, that is mg by m total mass. So, that is 2 by 8. So, that means x is equal to 0.25. So, the dryness fraction is this. Then we require the pressure. So, pressure can be calculated because it is saturated liquid vapor mixture. So, P saturated nothing but T saturated at 90 degree centigrade. So, from the book saturated temperature table, we can get the saturated pressure as 70.14 kPa. So, this number will get saturated temperature table of water. So, we got this pressure, then we are left with the volume. So, volume can be calculated, V is equal to mf into small vf plus mg into small vg. So, this small vf and vg can be calculated at 90 degree centigrade. We can have two values vf, vg from the saturated temperature table, and this number is 0.0136 meter cube per kg, that is for vf, and vg is 2.36 meter cube per kg. So, total V can be calculated because you know mf 6, mg 2, and when you put vf and vg, the volume would be 4.48 meter cube. So, it is a total volume. So, we are able to get the volume of the tank. The next simple problem, that is we expect to find out temperature of water at pressure 0.5 MPa and enthalpy 2890 kilojoule per kg. So, here the first thing that we want to check is that at 0.5 megapascal, what is its enthalpy Hg. So, this we can get from saturated pressure table. So, this number if you calculate for 0.5 megapascal, this number is 2748.7 kilojoule per kg. Now, here the enthalpy value is 2890. So, actual enthalpy is much more greater than Hg. So, this will tell you that this data refers to superheated steam. So, for superheated steam, then we have to find out the Clause's number for pressure 0.5 megapascal corresponding to temperatures at 200 degree centigrade. We will have this enthalpy about 2855.7. Now, when you for this same pressure, and if you look at temperature at 250 degree centigrade, we will have enthalpy value 2960.7. So, if you look at 2890 number, it is somewhere in between. So, this means through linear interpolation, we can extract temperature, actual temperature, which corresponds to H is equal to 2890, we will have about 218 degree centigrades. This is how you are going to refer the superheated table. And the last problem that I am going to use is for mass of air. So, here when you look at mass of air, what is given data? Volume 8 into 5 into 4. So, it is 160 meter cube. Okay. Let us say pressure is atmospheric 101.325 kPa. We require R, that is characteristics gas constant, that is 287 joule per kg Kelvin, and temperature it can be assumed as 300 degree Kelvin. So, you have to use simple equation m is equal to PV by RT. So, when you put these numbers, we will get about 188 kg. So, this is a very common way that in all our situations we are going to use the typical data value even if it is not given, and those numbers should be suitably assumed, and accordingly it can appropriate formula can be used to compute the numbers. So, with this I will conclude for the lecture today. Thank you for your attention.